This is exam 4 for Physics 101, Fall 2014. Wheel initially at rest. That is my angular speed. A wheel initially at rest rotates with constant angular acceleration of 2 radians per second squared. So omega naught is equal to 0, alpha is equal to 2 radians per second squared. And it goes through 16 radians of displacement. How long does it take to do that? Well, I know that theta equals omega naught t. Alpha t squared, omega naught is 0, so that whole term goes away. So I'm just left with 16 equals 1/2 of 2 times t squared. That is the square root of 16 is equal to t, which is 4 seconds. So B is the right answer. Potter's wheel moves from rest, so omega naught equals 0, to an angular speed of 8 revolutions per second. Omega equals 8. Alright, it's in revolutions, but notice my units here are in revolutions, so I'll leave it like that. T is 2 seconds. I want to know what is the angular acceleration. I know that omega equals omega naught plus alpha t. So alpha, since this is 0, alpha is just omega over t. That's 8 revolutions per second. Over my time, which is 2 seconds, that's 4 revolutions per second squared. That's C. Which of these is a measure of angular displacement? Okay, all 3 of these are proper units, 1, 2, and 3, but this is not. The arc, or arcs isn't even really a unit, but the arc is a measurement of distance, not of angle. So radians, degrees, and revolutions, that is C for number 3. 1 revolution is the same as how many radians? It's the same as 2 pi radians, so E for number 4. What is the angular velocity of a second hand on a clock? Okay, well, angular velocity is theta over time. The second hand of a clock goes through 2 pi radians. That's 1 full revolution in 60 seconds. 2 pi over 60, that's pi over 30. 6 over 30. Excuse me, which is approximately 3 over 30, which is about 0.1 radians per second. That was a question a student had submitted. If a wheel turns with constant angular speed, then which of these is true? Right. The angle through which the wheel turns in each second increases as time goes on. That's not true. In order for that to occur, we have to have alpha greater than 0. The angle through which the wheel turns in each second decreases as time goes on. Okay, likewise, that's not true. Alpha cannot be 0 in that case. Each point on its rim moves with constant acceleration. Okay, actually the acceleration is changing throughout time, because if I imagine this thing moving in this direction, up at this point my acceleration is in that direction. At this point my acceleration is in that direction. So it's not constant because the direction changes. The wheel turns through equal angles and equal times. Okay, that's what it means to have constant angular speed. And each point on the rim moves with constant velocity. For a similar reason as for part C, this is not true because the velocity vector is constantly changing. An object at rest begins to rotate with constant angular acceleration. If it has an angular velocity, omega, and time t, what is its angular velocity after time? Half t. Well, I know that omega equals alpha t. If I have my time, I have my velocity, so E is the right answer. Particle moves circular path of that radius and that speed. What is the acceleration? Okay, so first of all, I need to convert this for 5 revolutions per second. So radians per second. So that is 10 pi. I'm going to leave the pi because my answers are all in terms of pi. You could say it's 31.4 if you like, but I'll just leave it in terms of pi. And then this is omega. My centripetal acceleration is v squared over r, but since v is equal to omega r, this can also be omega squared r. So that is 10 pi squared times r, which is 0.1 meters. So that is 100 times 0.1, that's 10 pi squared. So that's the answer, which is E for number 8. What is the moment of inertia for a hula hoop with a mass of 1 kilogram and a diameter of 1 meter? Well, the moment of inertia for a hoop is just mr squared. That was on your table. The mass is 1 kilogram. The diameter is 1 meter, so it's 0.5 meters is the radius. 1 times a half squared is a quarter. So 0.25 is the right answer. That's A for 9. A 1,500 kilogram car, excuse me. I'll put those two together. 1,500 kilogram car rounds an unbanked curve with a radius of 52 meters and a speed of 12 meters per second. What minimum coefficient of friction must exist between the road and tires to prevent the car from slipping? Okay, well I know that my static friction is equal to my centripetal force, mv squared over r. Alright, that's mu times our normal force, which is mg, which is mv squared over r. My masses cancel. I'm looking now for mu, so I'm going to solve this for mu. It's v squared over gr. V is 12 over 10. The radius is 52. Let's see, that's 144 over 520. What is it, 0.18? No, 0.28, excuse me, 0.28. 144 over 520 is 0.28. Number 10 is C. Consider this bar. It can rotate about 3 points, A, B, or C. Which one has the greater moment of inertia? All right, the greater moment of inertia will occur here. And our moment of inertia is mr squared. So the one with more mass at larger radii will have the greater moment of inertia. And here I have mass all along this bar at longer radii than either here or here. So A is the right answer for number 11. Alright, what is the moment of inertia for this configuration of particles? Alright, well, this one doesn't contribute at all. So I is just this mass times the radius squared plus this mass times the radius squared. Since this is an equilateral triangle, I know that this distance is 4 meters. So my I will look like this, 3 kilograms times 4 meters squared. Plus the same again. That's 3 times 16 is 48, so it's 96. Just C, number 12. Consider this figure. What is the net torque? Rotating about point C. This provides no torque. This provides a, what is that at? They're both counterclockwise, so this is a positive torque 1, and this is a positive torque 2. Alright, those equal to 10 newtons times 2 meters times the sine of 30 plus 5 newtons times 4 meters times the sine of 90. Right, that's 10 plus a half is 5 plus 20. Excuse me. 20. 10 times 2 is 20 times a half. So that's 10 plus 20 equals 30 newton meters. It's positive, so it's counterclockwise. Alright, remember torque here is Fr sine theta. That's where I was coming. Fr sine theta. Here it was sine of 90, which is equal to 1. Consider rather than the previous question, has a mass of 3 kilograms. After 2 seconds, what is the angular velocity? Alright, so it has a mass of 3 kilograms. I is equal to 1/12 mv squared. That's for a rod rotating about its central axis. Okay, I just realized there's a mistake here, because the moment of inertia of a rod is 1/12 mv squared if it's rotating about this axis. So I'm going to rewrite this problem so that, let's see, I'm going to say instead that the rod has a moment of inertia equal to 4 kilogram meters squared. Right, so I'll rewrite this. The rod has a moment of inertia of 4 kilogram meters squared. So after 2 seconds of the torque acting on the rod, what is the rod's angular velocity? So if that's the moment of inertia, my torque equals I times alpha. So I can find alpha is torque over my moment of inertia. I've already found my torque, 30 newton meters over 4. kilogram meter squared. That's equal to 7.5 radians per second squared. And then if I want to know the angular velocity after 2 seconds, I just say omega equals alpha t, 7.5 times 2, which is equal to 15 radians per second, which is D for number 14. The bar has a moment of inertia of t kilogram meter squared and rotating at 3 revolutions per second. It engages with a flywheel, has a moment of inertia of 4 kilogram meter squared and is stationary. After they engage, they both move at the same speed. What is this new speed? Alright, so this is I initial, omega initial equals I final, omega final. Right, so I have a bar that's spinning at first, spinning about this axis, and then it's on a shaft or whatever, and then I engage it with a flywheel, and then they both spin at the same time. But when you bring them together, you increase the moment of inertia. So this is 2 kilogram meter squared, that's just the bar, times 3 revolutions per second, is equal to 2 plus 4 times omega final. So now I've added these two quantities. That's my new moment of inertia. So this is 6 times omega final. So omega final is 1 for number 15. Figure skater is rotating at 5 revolutions per second. Then she moves her arms out and is rotating at 10 revolutions per second. This should say actually moved her arms in. So which of these statements is true? Alright, well, she speeds up, so I know that I omega has to remain constant. So if this increases, then I know this has to decrease, is the moment of inertia. And it increases by a factor of 2, so she has to decrease that by a factor of 2. So B is the right answer for number 16. And again, as I said, she's moving her arms in, not out. Which of these is considered a fluid? Fluids are anything that flow, that's liquids and gases, 2 and 3. How many cubic meters of water and 300 kilograms of water? Well, the density is 1,000, that's on your table. I know that density equals mass over volume. I'm looking for the volume. Mass over density. I have 300 kilograms over 1,000. That's 3 over 10, or 0.3. A is the right answer for number 18. Okay, hydraulic lift. I have a force over here of 100 newtons and an area of 0.01 meters squared. And over here I have an area of 1 meter squared. And I want to know what is this force. So I know that by Pascal's principle, the pressure in is equal to the pressure out. That is that F1 over A1 equals F2 over A2. F1 is 100 over 0.01. That's equal to F2 over 1. 100 over 0.01 is what, 10,000. So number 19 is B, solving that for F2. Pascal's principle, all right, not this, that's for Archimedes' principle. This is Pascal's principle. A change in pressure at one point in an incompressible fluid is felt at every other point in the fluid. This is Bernoulli's principle, and this just isn't true. That's not anything. Alright, a tendon in your arm without any pressure on it has a length of 0.1 meters or 10 centimeters. There's the area. How much does it stretch when you have 100 newtons applied? And there's the Young's modulus. I'm probably going to take this away because it's in your table. Alright, so I have, and actually I'm going to change this just so you're not confused. So we just have that. How much does it stretch? In centimeters. So I have stress is equal to my Young's modulus times my strain, delta L over L. The stress is the force over area, that's 100 newtons, over the cross-sectional area, 7.5 times 10 to the minus 5 square meters. That's equal to the Young's modulus, which is 2 times 10 to the 7th newtons per square meter. Okay, sorry for the interruption. Let's see. So that's my Young's modulus, 2 times 10 to the 7th newtons per square meter. Delta L, that's what I want to know. How much does it stretch? And the original length was 0.1 meters, 10 centimeters. So you have this tendon in your arm. It's 10 centimeters long. And I want to know how much does it stretch. Let's see. So I have 100 divided by... I get 0.007... meters. That's delta L. But I want it in centimeters, notice. In fact, that's not an option here. So to get it into centimeters, I move it over twice. So it's 0.7. So 21 is B. Figure shows a barometer. If it's filled with water, what is the height when the pressure is 0.2 atmospheres? Alright, so I know that P equals P naught plus rho GH. In a barometer, as I have it here, this P naught is equal to 0, so it's just rho GH. The density is that of water. That's 1,000 kilograms per cubic meter. That's on your table. G is 10 meters per second squared. And then H, well, H is what I'm looking for. P over here is 0.2 atmospheres. That's 0.2 times 10 to the 5th. You have to convert that to pascals. From 1 atmosphere is 1 times 10 to the 5th. So that's 0.2 times 10 to the 5th. 20,000 divided by 10,000, which is 2 meters. So H equals 2. So number 22 is C. 23, a blood platelet drifts along with a flow of blood. It's partially blocked. The artery, as it moves into the narrow region, the blood pressure decreases. So we have this artery, it's blocked. I have this blood that's traveling along at a certain velocity. When it goes through here, it gets a bigger velocity, so the pressure decreases by Bernoulli's principle. The continuity equation is based on the conservation of matter. Conservation of energy is Bernoulli's principle, not the continuity equation. Ping pong ball has the average density and a volume of that. If the ball is completely submerged in water, what is the buoyant force? Okay, just plugging in numbers here, though you got to be careful because I give the density of the ping pong ball, but that's irrelevant. This is the density of the fluid times the volume of the object times G. It's in water, so that's 1,000. Sorry. 1,000 times the volume of the object, which is 3 times 10 to the minus 5 cubic meters, times 10. So it's 10,000 times 3 times 10 to the minus 5. And I get 0.3 newtons, so D is number 25. And what's the relationship between P and P naught? Okay, well, P is less than P naught, so C is the right answer. You know that because the level of this fluid is lower than the level of this fluid, so P is smaller than P naught, so it's not able to push that fluid down any further. Water flows through a pipe at 3 meters per second, cross-sectional area. It gets bigger. What is the speed of the pipe? Water through the larger pipe. So I have this situation. This pipe looks like this. It travels at 3 meters per second here. It's going to travel with a smaller velocity here. That's continuity equation. A1V1 equals A2V2. A1 is 0.5 meters squared. That's 3 meters per second. The near area is 1 square meter times V2. So that's 1.5 meters per second. C is the right answer.